Hi, this is Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. So in this lecture, we are going to discuss about the floating point arithmetic operations. So in previous lecture, we have seen arithmetic addition and subtraction on fixed point numbers. So in this lecture, we are going to see how to perform the floating point arithmetic operations. How to perform the arithmetic operations on floating point numbers. So a floating point number in computer register, it consists of mainly two parts. So any floating point number, it can be represented in two parts. That is, one is mantissa. So the mantissa, it can be represented with m, and the exponent, it is represented with e. So using these two parts, we can represent a floating point number. So the two parts represents a number obtained from multiplying m times a radix or raised to the value of e. So that means m. So mantissa m is multiplied with multiplied m times to the radix raised to the value of e. So that is m into r power e. So this is a representation of the floating point number. So here this m mantissa. So mantissa, it could be a integer value or it could be a floating value. So that means a decimal value like 0.1245 or something 12. So sometimes this mantissa we can also represent in integers or decimal value points. So this is a mantissa. And coming to the exponent, so this exponent should be in integer. It should not be a floating point number. So in this way we can represent the floating point numbers. So for example, assume a fraction representation under a radix 10. The decimal number 537.25. So this is a decimal number. So it is represented in a register with the mantissa 53,725 and exponent is equal to 3. So this is interpreted to represent the floating point number. So if the mantissa is equal to 53,725 and exponent is equal to 3, then how that we can represent in the floating point number. So in floating point representation, we can represent 0.53725 into 10 to the power of 3. So that is a representation of the floating point number. So mainly here in this arithmetic operation, that means arithmetic operations, we have mainly four types are there, that are addition, subtraction, multiplication and division. So these are the four basic arithmetic operations. So in this session we will see how to perform all these arithmetic operations on floating point numbers. So let's start with floating point addition and subtraction. So this is the first one, floating point addition and subtraction. So during addition or subtraction, two floating point operands are stored in accumulator register AC and another register BR. So these are the two registers we are going to store the data. The sum or difference is formed in accumulator. So once we performed addition or subtraction, then automatically the result will be stored in the accumulator register itself. So here mainly for this addition and subtraction, we are using two registers. One is a accumulator and another one is the BR register. So using these two registers, we are performing addition and subtraction. So this floating point addition and subtraction algorithm can be divided into four consecutive parts. So entire the algorithm of this floating point addition and subtraction, we are dividing into four consecutive parts. So that are, the first part is check for zeros. Check for zeros. So check for zeros. First we have to check any of the input is zero or not. Okay. So see here. So these are the two registers we are using. So suppose if the AC contains a zero value and BR it doesn't it contains some 0.1234 into 10 to the power of 2. So like that. So what it gives, so if AC value is equal to 0, that means one of the input is 0. So the result will be the result. So addition, here we are performing addition. So that means the value of BR register we are adding with the contents of the accumulator register. So that means the result will be BR register. The result value is equal to the value of the BR register. So BR register value will be transferred to the accumulator, because after performing any arithmetic operation, the result will be stored in the accumulator register. Okay. Similarly, if you take another case, so AC is having some value 0.825 into 10 to the power of 4, and BR is equal to 0. So that means now the BR register content is 0. But in previous case, the accumulator register content is 0. Okay. So now the result is AC. The result value is equal to the contents of the accumulator. And this accumulator contents, it will be stored in the accumulator itself. Okay. And also, if both accumulator and BR register both contains 0, then the result will be 0. And the result will be stored in the accumulator register AC. And similarly, we can also perform the subtraction also. Suppose if you are subtracting BR register content from the accumulator. So let us assume AC is equal to 0, BR is equal to 0.123 into 10 to the power of 2. So now the result is equal to the BR and it will be stored in the accumulator. But the sign will be negative. The result sign will be negative. Okay. So in this way, the first we have to check for the zeros. So suppose if both are non-zero values, then we are going for the next step is align the mantisas. Align the mantisas. And the third one is add or subtract the mantisas. And the last one is normalize the result. So we have seen the first part, that is a check for zeros. So these are in this way, first we have to check for the zeros. After that, align the mantissa. So see here. So here we are considering two numbers, two floating point numbers. So first number is the A. So already we know the floating point number, it can be represented with the mantissa and exponent. So the first number mantissa is let us assume M1, and the exponent of the first number is first floating point number is E1. So the first floating point number is 1.75 into 10 to the power of 2. And the second number is it is represented with B, and it's a representation in floating point M2 into R power E2. So M2 is the mantissa 2 and the second number exponent E2. So the second floating point number is 6.8 into 10 to the power of 4. Okay, so here we are assume E1 is less than or equal to E2. So that means E2 power exponent of second number is larger than the first exponent value. So we have finished the first part, that is checking for zeros. Second one is after checking zeros, then we have to align the mantissa. So see here. So suppose in the first step, if both accumulator register and BR register both contains 0, then the result is 0, nothing to do, and the result will be stored in the accumulator register. But when any one of the register is having some finite value, then we have to align the mantissas. We have to, so when both the registers contains a finite value like this one. So A is equal to 1.75 into 10 power 2 and B is equal to 6.8 into 10 to the power of 4. So when the both registers are having some finite value, then we have to align the mantissa. We have to align. So for that, select the number with a smaller exponent and shift its mantissa. Write a number of steps equal to the difference in exponents. So here, what is the exponent of the first number? 2. What is the exponent of the second number? 4. So what is the difference? So 4 minus 2. So that is equal to 2. So the difference in exponents is 2. Okay. So see here. So for that, first we have to select the smaller exponent value number. So that is nothing but we have to select this first number. Then we have to perform a shift right operation by 2 positions. Okay. So see here. So for example, if the number 1.75 into 10 power 2 and 6.8 into 10 power 4. So out of these two numbers, the smaller exponent value is the first number. So for that reason, I have chosen the first number. And I am performing shift right operation by 2 bits. So that it will become, so the first number is 1.75 into 10 power 2. So if I perform 1 bit right shift, it will become 0.175. So shift right. So we are performing shift right operation. So when we are performing shift right operation, the zeros will be added in the left side. So that's why 1 0 is there under decimal point, and this one will be moved to right side. So 175 into. So what about the exponent? When we perform shift right operation, its exponent value will be incremented by 1. So now it will become 10 power 3. So this is for one shift. For second shift, another shift. So 0.0175 into 10 power 4. Because once again, if you perform shift right operation, 1 more 0 will be added at the left side and exponent value will be incremented by 1. Okay, so this is so after performing shift right operation by 2 positions, then the A value will become this one. Okay, so because here, if you observe both the numbers now, the powers, the exponents of the both numbers are same. The exponents of the both numbers are same, 10 power 4. Okay, so now we can perform the operation. What the operation? Add or subtract the mantissas. Now we can add their mantissas. So what is the first number? So the first number after performing shift right, so 0.0175 into 10 to the power 4. What is the second number? 6.8 into 10 to the power 4. So now I am performing addition or subtraction. So I am considering addition. So addition. So see here. So 5, 7, 1, 8.6. So exponents are 10 power 4 because the exponents of both the numbers are same. So that's why 10 power 4. So this is a result. So where this result will be stored? Again, after performing arithmetic operation, the result will be stored in the accumulator register. So this is a result. Okay. So after performing addition or subtraction operation. So mantissa. So these are the mantissas. So these mantissas we have to add or subtract. Depends upon the operation. Okay. So this is a third part. And coming to the last part, that is a normalize the result if necessary. So what is normalization? See here. So in this floating point number, after a decimal point. Okay. So if this after decimal point, if it is having a non-zero value, then that is a normalized result. Suppose if it is having some 0.0685, some 10 power 2. So this is a not normalized result, because here after a decimal point, so we have a zero value. So this is not normalized. So we have to convert into the normalized. We have to make it normalized. Okay. So what we can do? So for that purpose, see here. So this result, the result is a 6.8175 into 10 to the power 4. So here 6 point. So it is a overflow. So here overflow is occurred. So this is 6. So this is the overflow. So in order to overcome that overflow, we have to perform a shift right operation. Shift right. So if you perform shift right operation by one position, it will become 0.6817 into 10 to the power of 5. Because when you perform one shift right operation, the exponent value will be incremented by 1. And similarly, if you perform shift left operation, the exponent value will be decremented by 1. So that is a concept here. So here I performed a shift right operation, so that the exponent value will be incremented by 1, so that it becomes 5. So this is a normalized result. So because after decimal point I have a non-zero value, so this is a normalized result, and also it doesn't have any overflow, because I performed a shift right operation to the previous result. So this is about the floating point addition and subtraction. And coming to the multiplication algorithm. So multiplication of two fixed point binary numbers is in signed magnitude representation is done with paper and pencil by a process of successive shift and add operations. So this multiplication algorithm, it is similar to the multiplication done with paper and pencil. So how we are doing with decimal numbers? So this is similar. So the process, it consists of looking at successive bits of the multiplier. So here we have two numbers in order to perform the multiplication. One is a multiplicand and another one is a multiplier. So first we have to look into the bits of the multiplier and the least significant bit first. So this is a multiplier. In that multiplier, what is the least significant bit? So this is a least significant bit. So if your multiplier bit is 1, so if the multiplier bit is 1, then the multiplicand will be copied down. So multiplicand. So now multiplicand is copied down. Otherwise, so zeros will be copied down. Suppose if the multiplier bit is 0, so what we can copy? We can copy all the zeros. Okay, so if the multiplier bit is equal to 1, the multiplicand is copied. Otherwise, zeros will be copied. So the numbers copied down in successive lines are shifted one position to the left from the previous number. So every time the bits are copied, one position will be shifted left. So when you compare these two, so the bottom number of bits will be shifted left side by one position. So in this way, all the multiplicands will be copied down. And finally, the numbers are added and their sum forms the product. So finally, we have to add all these numbers so that the final product will be formed. So this is the final product. Okay, so this is how a general multiplication algorithm takes place. So coming to the hardware implementation. Hardware implementation for multiplication of two floating point numbers in signed magnitude form. So we have a two numbers, two floating point numbers. So let us assume, see here, we have a two floating point numbers A and B. So these are the two numbers. So the magnitude of A, it will be stored in A register, and the magnitude of A, the sign of the A register will be stored in the AES. Similarly, the magnitude of B register will be stored in B register, and the sign of the B register will be stored in the B suffix S register. And we are storing the result by combining this A register and Q register. So if any exponent is there, a remainder is there, if any quotient is there, then that we can store in the Q register. So in order to implement this hardware, so total we require one sequence counter, one complementer, one parallel adder, and 3 registers: B register, A register, Q register. So total 3 registers and 4 flip-flops in order to store the sign of the numbers. So this is one flip-flop, second flip-flop, third flip-flop, this is fourth flip-flop. So total. So this is a hardware we require. So one sequence counter, one parallel adder, one complementer, 3 registers, and 4 flip-flops. Okay. So see here. So this is a sequence counter. So in sequence counter, we will load the value which is equal to the number of bits in the multiplier. So n that means n minus 1. So n minus 1 will be stored in the sequence counter, and it is a B register. It is complementer and adder, A register. So see here. So here we are multiplying. See here. We are multiplying 2 numbers. So that means A and B. So we are multiplying 2 numbers, and the result will be stored in this A and Q. Okay. So see here, because here suppose if you consider any 4-bit register, so A is a 4-bit register, B also 4-bit register. So if you multiply any 4-bit numbers, so the result will be 8 bits. So result will be 8 bits. So that's why here 2 registers we are using, Q register and A register. So in previous scenario, so see here. So each number is represented with a 5-bit. So we have multiplied 2 5-bit numbers. So it results 10-bit. So see here. So it results a 10-bit result. So similarly here also, if you multiply any 4-bit numbers, it gives a 8-bit number. So in order to store this, we are using a 2 registers. Okay. So upper 4 bits will be stored in the A register, and lower 4 bits will be stored in the Q register. So here we are using different hardware. So Q register and QS, it contains multiplier and its sign, multiplier and its sign. Sequence counter, it is used to set value equal to the number of bits in the multiplier. B register and BS flip-flop, so it contains the multiplicand and its sign. So in B register we are storing multiplicand and its sign. So when you are performing multiplication, we have multiplicand and multiplier. So we are multiplying the multiplier with the multiplicand. Okay. So the multiplier. So multiplier will be stored in the Q register, and multiplicand it will be stored in the B register. So we are multiplying Q with B. Once we perform the multiplication, the result will be stored in the AQ. So in Q, the lower bits will be stored in the Q register, and the upper bits will be stored in the accumulator register. So A register and E flip-flop. Initialize it to 0. AS denotes the sign of the partial product. EA held partial product. So EA held partial product because in A accumulator it stores the upper product. Okay, it stores the upper bits of the result. So that's why it can be used to store the partial product, with the carry generated in addition being shifted to E. So in addition to that, if is there any carry, that will be stored in the E flip flop. And Qn is the right most bit of the multiplier. So AQ, it will contains the final product. A holding the most significant bits and Q holding the least significant bits. So here in this Q, in the Q register, we have a multiplier. In B register, we have multiplicand. So we are performing a multiplication operation, and the final product will be stored in these two registers. So coming to the floating point multiplication. So during multiplication, the two floating point operands are in BR register and QR register. So the product is formed in AC. The product is formed in AC. Okay. So see here. So the algorithm, it can be divided into different parts. So first one is a check for zeros and then add exponents, then multiply the mantisas, and the last one is a normalize the result. So these are the different parts of the algorithm. So uh, this is a algorithm of the floating point multiplication. So here, for better understanding, consider a floating point numbers BR, QR. So BR is equal to 1.75 into 10 power 2, and QR register is equal to 6.8 into 10 power 4. So BR register, it is represented with M1 into R power B. So the exponent of B register is B, small b, and the exponent of the QR register is small q. Okay, and the result. So after performing, where the result will be stored? The result will be stored in the AQ register. The result will be stored in the AQ. AQ is a combination of accumulator register and the Q register. Okay, so this is okay. So coming to the this algorithm. So we are performing a multiplication algorithm. So in multiplication, the in BR register, we are storing the multiplicand, and in QR register we are storing multiplier. So multiplier is stored in QR and multiplicand is stored in BR register. Okay. After that, so what is the steps in algorithm? What is the first step? We have to check for zeros. We have to check for zeros. So we are multiplying. So QR is multiplying with BR. So first we have to check for zeros. Is there any one of the register is having zero value or not? So suppose first we are checking BR register. If BR register is equal to 0, so if BR register is equal to 0 and QR is having some non-zero value, so what it results? So this is a multiplication. If any one value is 0, then ultimately the final result also becomes 0. So 0, the result is 0. So the result will be stored in the AQ. Okay, so that means the result is 0. If BR is equal to 0, the result is 0. So that's why the accumulator, it stores a value 0, so that the operation will be ended. So nothing to do. If any one of the value is 0, then operation will be ended. Okay, suppose if the BR is not equal to 0, if BR is not equal to 0, then we have to check the QR. Okay, so see here, consider the second case. So now BR is having some 1.75 into 10 power 2. Now QR is equal to 0. What is the result? Even BR having some finite value, the QR is 0. So you will get 0 value, because in multiplication, if any one value is 0, the final result will be 0 only. So again the result is 0. So that the result 0 value will be loaded into accumulator. Okay. So that's why first we have to check for zeros. Okay. After that, so suppose if Q are also having non-zero value, so that means the Q are also having some finite value. So that is 6.8 into 10 power 4. So now in this case, both the numbers and both the registers or values are not are non-zeros. That means both are having some finite values. So when after checking zeros, then if both the registers are having non-zero values, then only we are proceeding to the multiplication. So if B are not equal to 0, Q are not equal to 0, then add exponents. What is the second part of the exponent? Add exponents. So what is the exponent of the BR register small b? What is the exponent of the QR register Q? So can we perform addition between B and Q? Can we perform addition between the B and Q? We cannot perform, because if you look into the previous one, this hardware implementation, so we have a adder here. We have a adder here. So this adder is present between the B register and A register. So this adder is not in connection with the this Q register. So that's why we cannot perform the addition between A and Q. So we cannot perform addition between this B and Q. So we can perform addition between A and B. So that's why what we are doing. So the exponent this Q, we are shifting to the A register. So this one. So the exponent of this Q will be loading into the A. So we are loading into the A. After that we are adding. So now the Q, so the exponent of the QR register will be available at A, and the exponent of B register is available in B register, small b register. So now we can add these two. So we are performing a addition operation, and the final result will be stored in the small a. Okay, so that is the second part, add exponents. What is the third one? Multiply the mantisas. Once we have added exponents, then we have to add the we have to multiply the mantisas, because in multiplication the exponents are adding. So that's why here we are adding the exponents. So after adding, so add exponents. What is the add exponent? So a value is the 4, a value is 4, b value is equal to 2. 4 plus 2, 6. So in A, what is the value stored? 6. So now the exponent power, the final product power is 6. Okay. Now multiply the mantisas. Now we can multiply the mantisas. So what is the mantissa of the first number BR register? 1.75. What is the mantissa of the QR register? 6.8. After multiplication, the final product will be 11.9. 11.9. Okay. Now we are checking A1. So see here. So in this A1, is there any underflow? Suppose see here, the result is 11.9 into 10 power 6. But here in multiplication, there may be a chance of getting underflow. Underflow is nothing but, see here. Let us assume if the result is having like this. 11.09 into 10 power 6. Okay. So see here, after a decimal point, we have a 0. So that 0 means it is a underflow. Underflow. If the result is like this, 11.09 into 10 power 6, so it indicates that there is an underflow. If underflow is there, what we have to do? We have to perform a shift left operation. Shift left operation. So if you perform shift left operation, what will happen? So this 0 will move to left side. So it will become 0.9. 0.9 into 10 power 6. That means here the underflow is rectified, removed. So underflow problem overcome here by performing the shift left operation. So here, underflow problem overcome here. Now the exponent. So when we perform shift left operation, the exponent value will be reduced or decremented by 1. So this 6 minus 1. So it becomes 5. So now the exponent, it becomes 5. So that means what is the exponent of the result a? What is the exponent of the result a? Small a. So it will be decremented by 1. So a minus 1. So see here. So exponent is decremented by 1 and the final 5. So 6 minus 1, 5. So 5 will be stored in the small a. And we are performing a shift left operation on the data which is stored in the AQ. Okay. And the result will be, and the operation will be finished. Suppose if the A1 is equal to 1, if the A1 is equal to 1, so if the A1 is equal to 1, then we can end it. Suppose if A1 is equal to 0, then we are performing a shift left operation, then we are decrementing the exponent power, we are decrementing the exponent, then the operation will be ended. Okay. So here in this, see here. So here it is a non-zero value. It is a non-zero value. So no overflow is occurred. So that's why directly the operation will be ended. Suppose if there is any underflow occurred, then only the control will be flow in this way. Okay. So this is a floating point multiplication between any two registers. So see here. So this is a circuit. So this is a reason. So why we have transferred the Q value into the A, because we cannot perform addition in between the Q and B. So that's why the Q value will be shifted into A, so that we can perform the addition between this A register and B register. And coming to the floating point division. So during division, the dividend is in AC accumulator and the divisor is in BR register. So similarly, this division algorithm also, it has divided into different parts. The first one is a check for zeros and then initialize the registers and evaluate the sign, align the dividend or dividend overflow, subtract the exponents or divide the matrices. So these are the different parts. First part is a check for zeros. So first we have to check for any zero. Is there a dividend or divisor is 0 or not. After checking, initialize the registers and we have to evaluate the sign of the quotient and align the dividend. We have to align and we have to align the dividend or dividend overflow. Subtract the exponents, because in division we are subtracting the exponents. In multiplication we are adding the exponents. And finally we have to divide the matrices. So the two operands are checked for zeros. So we have to check the operands first. So here, see, so if the divisor is so we have so dividend is in AC and the divisor is in BR. So this is divisor. So this is dividend. Okay. So see here, if the divisor is 0, so first one is if the divisor. So if the BR contains a 0 value, this indicates an attempt to divide by 0. So it indicates that divide a number by 0. So if you try to divide any number by 0, so it gives an error. It gives an error. So what is an error? Divide by an 0 error. So it is an illegal operation because we cannot divide any number by 0. So that's why it is a illegal operation. So if the BR register, if the divisor is 0, it will show a error message. Okay, so that is illegal operation. The operation is terminated with an error message. So if the divisor is 0, nothing to do. So simply it will show an error message and it will terminate the operation. And an alternative procedure would be set the quotient in QR to the most positive number and or to the most negative number if the dividend is negative. So if the dividend is negative, we can store a most negative possible. Similarly, we can store a most positive number possible in QR. Oh, okay, so that is the first case. That is when divisor is 0. The second case is when the dividend is 0. So this is the second case. If the dividend is 0, the quotient in QR is made 0 and the operation terminates. So suppose if the dividend is 0 and we have a finite value of divisor. So what will happen? It gives a it results a quotient QR made 0. Quotient will become 0 and the operation will be terminated. And the third case is if the operands are not 0. So suppose if both the dividend and divisor are not zeros, then we can proceed to the division operation. And also we have to determine the sign of the quotient and store the sign of the quotient in the QS register. The sign of the dividend in the AS is left unchanged to be the sign of the remainder. So the sign of the A register we are not changing because it will be the sign of the remainder. The Q register is cleared and the sequence counter SC is set to a number equal to the number of bits in the quotient. So first we have to check all these three cases. So first one is there if the divisor is 0, and the second one is if the dividend is 0, and the third one is if both the dividend and the divisor are not equal to 0. So see here. So first check for zeros. So that we have seen. Check for zeros. So first the divisor. So the divisor is in BR register and the dividend is stored in the accumulator register. So what we are performing? We are performing a division operation. So first we are checking divisor. Okay, first we are checking divisor. So first we are checking divisor. So what is divisor? The divisor is stored in the register BR. So we are checking is the BR is equal to 0 or not equal to 0. So what will happen if the divisor is 0? If divisor is 0, what it will show? It will show an error message that divide by 0. So if it is equal to 0, it will show a error. If BR register is having 0, it will show a error. What is the error message? That is divide by 0. Then the operation will be terminated. Suppose if the divisor is not equal to 0, then we are checking dividend. We are checking the dividend. So the dividend is stored in accumulator register. So if the accumulator, we are checking whether the dividend is equal to 0 or not equal to 0. So if the dividend is 0, what will happen? If the dividend is 0, then the 0 will be loaded into quotient. The 0 will be loaded into the quotient. Then the operation will be terminated. And if the dividend is not equal to 0, so if the divisor not equal to 0, dividend is not equal to 0, then we have to perform. So what is the second step? Initialize the registers. If both the divisor and the dividend are not equal to 0, then we have to initialize the registers and we have to evaluate the sign of the quotient. So see here. So how we are evaluating the sign of the quotient? So by performing exclusive OR operation between the signs of the divisor and dividend. So already we know. So the divisor is in BR register and dividend is in the accumulator register. So the sign of the dividend is in AS and the sign of the divisor is in BS. So now in between these two registers, we are performing a XOR operation. In between these two, we are performing a XOR operation. So what is XOR operation? If it is having same inputs, it gives a output 0. If the inputs are different, output is 1. So that is an exclusive OR operation. So here, suppose if both the number registers, so that is this is AS, BS, and output. So if the both numbers are positive, so positive means same. If both numbers are positive, same, it gives a 0. Okay, so it gives a 0. So that means if the numbers are having same sign, then it will be the sign of the quotient is positive. If the signs are different, like 1, 0, 0, 1, that means if one number is positive, another number is negative. And similarly, one number is negative, another number is positive. In those case, the quotient of the sign of the quotient is negative. Okay, so in that way, we are determining the sign of the quotient. So that is AS XOR with BS. So result, that sign will be stored in the QS. After determining the sign, that resultant sign will be stored in the QS. And we are loading zeros with Q. We are loading 0 with the Q. Because initially, the quotient is 0. So that's why zeros we are loading into the quotient register Q. And the number of zeros that are equal to the size of the register. Suppose if the size of the register is 8-bit, then we have to load 8 zeros into the Q register. Next, sequence counter. So in sequence counter, it is loaded with the count. So that count is equal to the n minus 1. Because this is a sign magnitude representation. So in sign magnitude representation, the first bit is it is used to represent the sign. and the remaining bits are used to represent the magnitude. So that's why the sign bit is 1 bit. So if the total number of bits is n, so we are neglecting the sign. So that's why n minus 1. So n minus 1 count is loaded into the sequence counter. Okay. So after that, we are performing subtraction. After that, align the dividend or divide overflow. So we are aligning the dividend. So for that purpose, we have to subtract the divisor from the dividend. So here, this one. So here division. So here we are doing we are performing subtraction operation. Okay. So in order to align the dividend, we have to subtract the divisor from the dividend. Okay. So here, what is this? So B is a divisor. So that means here we are doing a 2's complement. So 2's complement here. First we are finding the 1's complement of the B register, that is nothing but B bar, and then we are adding 1 to that. So B bar plus 1. This we are adding to the dividend. Okay, so that the dividend will be aligned, and that result will be stored in EA. And after that we are checking, is there any dividend overflow? So E is it is a overflow. So when overflow will occur, if A is less than B. If A is less than B, then okay. So if A is less than B, there is no overflow. Okay. So what it indicates? So overflow is equal to 0. So it indicates that we can subtract the exponents. So that means if overflow is equal to 0, it represents we are making correct flow. So that means it is ready to divide. Okay. So now subtract the exponents. So in order to subtract the exponents, we have to restore the value of A. So how we can restore? So here previously we have subtracted B. We have subtracted the B value from A. Now we have to restore the value of A. So that means previously we have subtracted. Now we have to add. So that's why the contents of B register are added with the A, and the result will be stored in the accumulator A. Okay. Suppose if there is any overflow. So see here. If there is any overflow, we have to perform a shift right operation. Okay, shift right operation. So before performing shift right operation, here also we have to restore the value of the dividend. So the dividend is in accumulator A. Okay. So once we have restored the dividend, then we need to perform the shift right operation. So shift right A. Once you perform shift right operation, the exponent value will be incremented by 1. So exponent of the dividend is in small a. So that's why A plus 1 will be loaded into the A. After that, we are subtracting the exponents. Okay. So what is the exponent of the dividend? So exponent of dividend is small a. Exponent of divisor is small b. So we have to subtract their exponents because we are performing a division. So AC by BR. So AC exponent is small a. The exponent of BR is B. Okay. So we are performing A minus B. So how we can perform subtraction? So by taking 2's complement of the exponent of this B. So that means how we can represent the 2's complement value. So first we have to take the 1's complement, so b bar. For that we have to add 1, so that is equal to 2's complement. So this we are adding with a. So this entire, that is equal to a minus b. So that means their exponents are subtracted. Okay. So once their exponents are subtracted, then we have to store that. So the final result will be stored in the a. Final result will be stored in the a. Okay. So final result will be stored in the a. So that a, it will be that exponent, final exponent, it will be copied to the q. Okay. So q is a exponent of the quotient. Exponent of the quotient. Okay. So here it is no need of bias. So a plus bias. So here we are adding some bias to the exponent of the dividend. Okay. And finally, after subtracting the exponents, then we are dividing. We are dividing the magnitude. And finally, the operation will be ended. So the final quotient will be available in the QR. So the final quotient will be available in the QR, and the exponent will be available in small q. So this one. Okay. So we are dividing the matrices. So this is a division algorithm for the floating point numbers. Okay. So in this lecture, so we have discussed about the various arithmetic operations like addition, subtraction, multiplication, and division on the floating point numbers. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.